Okay, Nina and Julie, I'm going to explain the homework here. This is a nifty little tool called Doodlecast, and so you'll be able to hear me and watch as I draw some things on the graphs. So section 1.9 is about interpreting and making graphs that correlate to real-life situations. So in number 4, you see that a plane is at the spot where it would pick up passengers, and so the plane is not moving, and passengers are getting on the plane, and then the plane leaves the terminal and it moves out to the runway, so it drives slowly, and then it sits in the runway and waits for clearance, and then when it has clearance, then the plane will accelerate very sharply, and then it will take off at a very high speed. And so looking at table 1, table 2, and table 3, for the starting speed, we know that the passengers are getting on the plane, so the speed is going to either be 0 or nothing else. So it's going to be table 1 or table 3. And so right now we've narrowed it down so that the answer is either table 1 or table 3. And so as we look at these tables, take a look at table 1. At 6:10, at the time 6:10, the plane's moving at 20 miles per hour, and then at 6:20 it's moving at 40 miles per hour, and then 0, and then 80 miles per hour. Well, 80 miles per hour is fast, but it's probably not fast enough to take off from the runway. So we look at number 3. It moves at 10 miles per hour, which seems like a reasonable speed just to go out to the runway. And then we see 0, where the plane stops, and then we see 80, and then 350. So 350 seems like a reasonable speed that the plane would accelerate to as it ascends into the air. So we're going to pick table number 3 for our answer for number 4. And now moving down to number 5, tell which graph corresponds to each table described in exercise 4. Okay, so we're going to make a simple coordinate graph, and since time and speed are both positive, we're just going to deal with the upper right-hand corner of the coordinate graph. And so the x-axis represents time, and the y-axis represents our speed. I hope it's alright if I just write an S for speed. And here at the cross of the x and y-axis, that's where the graph equals 0. And so as time goes on, we go from 6 o'clock to 6:40 at the end. Okay. I apologize, it's a little sloppy. So as the plane begins at 6 o'clock, the plane's speed is 0, so we'll make a mark at 0. And then it moves to 10 miles per hour. So the fastest the plane goes is 350 miles per hour. So let's make a mark up here at 350. And so 10 would be pretty low on the graph. And then we'll make a mark at 10. And the plane stops again. And then it accelerates to 80 miles per hour, which is about 8 times as fast as 10. So we'll move up here. And then the plane finishes at 350 miles per hour, which is exceedingly more than 80. And so there's going to be a steep incline. As we connect the points, and as you go back and explain what the graph says, it says that it starts at 0, there's an acceleration, and then it stops again here at 0. Make a point of that. At 0, and then it accelerates, and then it accelerates very rapidly. And so that would simulate what a plane looks like as it leaves the runway. So as we look at the graphs, graph number 1, 2, and 3, and number 5, it looks like both graph number 1, 2, and 3, that all of them start at 0, but only one of them is really going to look like our graph. So you just have to use a little bit of intuition, and it looks like graph number 3 doesn't really accelerate at the beginning at all, right here. So let's cross that one out. And graph number 1 accelerates right here, but it doesn't really pick up that speed that would mark 350, which is a pretty great speed. So let's cross number 1 out. And as we look at number 2, Number 2 sort of matches our graph. It has a low 10 miles an hour here, and then it stops, and then it accelerates to 80 miles per hour, and then it really accelerates to 350 miles per hour here. So we'll say that graph number 2 best corresponds to the table described in exercise 4. In number 6, we're creating a graph that illustrates the information in the table about Mrs. Schwartz's commute from work to home. So there's only 2 columns here, and they've just repeated the same column twice. So we read the time in order from 5:12 to 5:13, so on until we get to 5:17. The speed of Mr. Schwartz as he commutes, he begins at 7 miles per hour, and then he goes to 35 miles per hour. So we could probably guess that he's in a car. And then he goes back to 8, and then to 46, and then to 12, and then to 0. So just visualize what that would look like as you are driving a car. So obviously if you're at 0 miles per hour, you're at a standstill. So you might be at a red light or a stop sign. And as you go up to 46 miles per hour, you might be on a more open road. And as you slow down to 12 miles per hour, maybe you're making a turn or something like that. But we don't need to know all that. All we need to do is make a graph. So we'll make a graph to the right, and we'll do that in orange. Again, this is kind of an abbreviated version. The x-axis, the horizontal axis, is going to be time, and the vertical y-axis is going to be his speed. So I'm not going to mark values for the time, but I'm just going to kind of move to the right as we evaluate this problem. So the fastest speed that he moves at is 46 miles per hour. So we'll make a mark on the graph for 46, and we won't go any higher than that. So he starts off by going 7 miles per hour, which is a pretty slow speed, so we'll make a mark down here. Then he increases to 35, which is going to be a little higher, and then back down to 8, and then up to 46, which is his fastest speed by far, and then 12, and then back down to 0. So we move to the right as time progresses. So as time increases on the x-axis, we just make the correct marks for what his speed is. And then we connect the dots. None of these marks are 0 until the very end. So he doesn't come to a complete stop until the end. And so that's what a graph would look like to illustrate Mr. Schwartz's commute from work to home. I hope you guys are safe as you're driving. Make sure to keep it under the speed limit. Number 7, use the table to graph the movement of an electronic security gate. Okay. Again, it's asking for a graph. So we'll draw a graph just like number 5 and 6. And we'll use time. The time is in equal increments from 0 to 5 minutes to 10 minutes to 15 minutes to 20 to 25 to 30 to 35. The gate opens, and so that would show that on the y-axis, and time is usually always showed on the x-axis. And using the examples from number 4 and 6, we can just replicate that and sort of do the same thing. So just to show an abbreviated version here, the video is going to be getting a little too long to send. We'll go from 0 to 3 to 6 to 9. It's increasing to 12, and it stays at 12 for a while, and it decreases back to 9. So again, that's a little bit of a sloppy graph. You can make some marks here on the y-axis here, and you could also mark what the actual time increments are on time. And so all those points, remember, they're called ordered pairs. An ordered pair is a combination of an x-coordinate and a y-coordinate. So 0 and 0 is an ordered pair. Time would be the x value. The gate opening would be the y value. The same for this ordered pair. we would write as 15.9, and all we do is write it on the correct spot on the graph, connect the points, and we'll have a graph like the top left here. Continue to do that for the rest of number 7, and you're good to go. Alright, I hope this video was helpful. Give any comments if you have them, and enjoy your night.
Made with Doodlecast Pro.